because this is more of an internship uh, series, or it's geared towards you, I would say, and not towards physicists per se. Or I also put in a little bit of background history on me. Don't normally do that in a talk, but I figured you all are here to learn also about how to have a career, maybe. This is a picture of me at Snow Lab. I've doctored the keep out, beyond the standard model thing. You'll see the actual image at the end. I like to sort of start off. This slide reminds me of my journey in a sense. And this is a story that somebody told me about Art McDonald, who got the Nobel Prize in 2015 on the snow experiment. And I'll talk about the snow experiment later. But it's sort of, this is the way I tell the story now. As a new postdoc arrives, just got his PhD, and he's going to now have a job for Art. And Art hands him a shovel and says, okay, we need to clear this debris. And he replies, wait, I have a PhD, thinking that that kind of work is beneath him. And Art's like, oh, so you don't know how to use a shovel. So basically, a lot of the work that I've done has actually been keeping experiments or building experiments running, keeping experiments running or building experiments. And there's a lot of what you might not think is traditional physics labor in that work. Okay, the outline of my talk, I sort of had to shoehorn this in, how I got here first. And then I'll talk about the neutrino history, and then I'll talk about sort of what I'm doing now at SLAC. So I actually did my undergrad internships doing lightning research. This was at New Mexico Tech. And it wasn't through any internship program. I just asked my mechanics professor, is he looking for students that work? And he said yes. And so I ended up working for him for 2 summers and a little bit during the semester as well. And I'll show you what we did. But we basically flew instruments inside lightning storms. So that was my undergrad. What did I actually do? Well, I did a lot of soldering. That probably is reminiscent of some of the jobs that you guys have. I designed some really basic circuitry that sort of allowed us to run these computers or these instruments off the wall until we were ready to launch them, and then we could just yank the cord out and then launch it, and it would stay online basically. I was interested in astronomy as a high schooler, and so I knew about telescopes. And one of the problems we had was we wanted to point an antenna at the instrument while it was flying through the air. So this guy's holding one of the instruments. The instrument has GPS on it, and it could communicate its location to us via radio. But we wanted some way to point the antenna at the instrument while it was flying. And so I was like, well, I knew these telescope bases existed. You would normally mount a telescope to it, and you could tell it where to point. And so that was a project then I took on basically as an undergrad intern. I helped build the instruments a little bit. So that's a picture of me building it. And here's an animation of a launch. So I also helped participate in launches. I'll let it play one more time. But basically, you can see the big helium balloon here, and attached to all the instruments, a GPS tracker, a baffle for keeping it vertical and stuff like that. So that was a lot of fun. And I also participated go out in a government truck, and we would have to go find where the instruments landed, inevitably on some farmer or rancher's yard. And so we would have to bring them a bottle of Crown Royal as a token of, as a gesture to trade for our instruments. Okay, but what did I actually learn as an undergrad? I would say I didn't understand anything about lightning physics, right? I kind of realized that that's not something I wanted to do as a grad student. It's not physics I wanted to learn. But I really enjoyed building stuff, circuitry, machinery, engineering. But I think I was driven by something a little more fundamental, right? And so it's a great time to learn what maybe you're interested in now, because you're going to have to pick soon, right? As a grad student, if you're going to go to grad school. And so I just have one slide on like the lessons learned when you apply to grad school. I blindly applied to 10 grad schools, and I got accepted into one. I thought I wanted to do AMO physics. It's called atomic molecular optics. So it's like shining lasers at atoms and then seeing, what you see basically from that. And what I didn't realize is that grad school is a advisor, and he's going to mentor you. It's this dichotomy where you actually are going to work for a person, they're going to train you. And so you need to reach out to those people that you want to work with, ask them about their research, make sure you're interested in it, but also you need to convey the fact that you're interested in working with a person at that school. And then you also need to ask if they have room. Not all professors have room to take students. So like I said, I got lucky that one school accepted me. The professor that I wanted to work with also was looking for people. And when I got accepted to the school, then I basically emailed them and said, you know, I'm coming to CSU. I would like to work in your lab. And he's like, great, actually, can you come earlier? I need people now. And so he actually paid me to work the summer before I even started courses at grad school. My thesis project, you know, like I said, I was going to be an ammo physicist. So I was shining lasers at things and seeing what they looked like. But it turned out that the project that we were working on was for these crazy particle physicists that were looking for neutrinoless double beta decay. And so the idea is when this decay happens, which no one's ever seen before, a xenon atom turns into a barium atom. And an AMO physicist like me could look for a barium atom in xenon and say, hey, it happened, or it didn't happen. So this is the lab we built. This was a classroom when I started grad school. We built a whole lab in there to do it. That's me working on the table where the optics and the xenon freezing thing was. This is at Colorado State University. Just some more pictures of sort of what I ended up having to build. So this is a window that held the xenon and barium that I can shine the lasers through. This is a barium source. I guess the laser pointer doesn't work on the screen, but the top thing is a barium source that I CAD'd up and then I built. And you know, at the end of the grad school, you typically make a publication or a couple publications of the work you did. And the work I did was identifying, you know, that we could see barium in xenon and what its spectral characteristics were like. And that's all great, but it wasn't actually what I was passionate about. So I made another pivot. And it turned out that, you know, as a part of this work, being a part of this EXO collaboration, doing this crazy particle physics experiment, that we were expected to contribute also to build the experiment. And we also got to look at the data. And I really fell in love with that, actually. And so I made another pivot basically to particle physics. This is the experiment we built. So this is underground in a salt mine in New Mexico. This is me and Jesse basically building out plumbing for some system. I don't know if anyone can read that, but somebody, while we were constructing the clean room, somebody wrote a sign that says Jesse eats monkey poo on the window that you couldn't actually, on the other side of the window. So once we installed stuff, you couldn't take it down. So that was there for a long time. We had a lot of fun down there. Okay, so why particle physics? Why did I fall in love with particle physics? Well, it doesn't get more fundamental. Everything in the universe is made from fundamental particles. This is sort of the standard model as we understand it, and all of the particles that do make up the universe. And there's really still a mystery of like what makes up the universe. This model down here sort of shows that of the standard model only is a small fraction of what we understand. So there's dark matter, we have no freaking clue. And there's dark energy. We know what dark energy is, but just most of the universe is still a mystery to us. And then the other aspect of it that I didn't really appreciate, and maybe you guys will get a sense of now, is the size of the collaborations sort of determines what you end up doing. Some collaborations are so big that most people only do data analysis. Medium-sized collaborations kind of expect everyone to participate in hardware and software, or vice versa. Maybe a very small experiment that's always on a benchtop, it's almost all hardware. And so for me, it was really appealing to be in this sort of big medium set where we built hardware and did a lot of analysis. Okay, so now I'm going to segue more or less to physics. And this is slides I sort of poached from other talks, so it's going to look more traditional, but the idea is, the universe is full of matter and presumably dark matter and no antimatter. So that's mysterious, right? It all came from pure energy. Everything must be conserved in the end. So we would expect the same number of matter particles as antimatter particles, but that's not the case. Now, the physics that you do has made it when you get an XKCD comic. I'll let you read it. So yeah, the problem is, where is all the antimatter? And presumably, if the laws, conservation laws that we understand were fixed, then there wouldn't be anything left in the universe now. Okay, so we've all seen this expansion model of the universe, and somewhere at the very, very beginning, we had to have had something called this baryon asymmetry, something that produced more matter than antimatter. And so ways we can study that is through neutrinoless double beta decay. So in traditional double beta decay, you produce an electron in an antineutrino, equal parts matter, antimatter. Double beta decay is a standard model process as well, produces an electron and antineutrino twice. Still all standard stuff. The thing we're looking for is this neutrinoless double beta decay. And the idea is the neutrinos can cancel each other out in the reaction, and that decay does not produce antimatter. And so there's a way to produce this asymmetry, basically. And this would just be one way to probe it. These are leptons and not bosons, but okay, so the mystery now appears to lie with neutrinos. So here's just a brief context for like particle physics history, right? We learned almost all of this from radioactive decay, in fact. So, Becquerel and the Curies discovered radioactivity in the late 1800s. Rutherford sort of figured out that there was multiple types of radioactive decay. There's alpha decay, beta decay. And then they sort of map this now to the periodic table, realizing that there's protons in the nucleus, basically, and that the nucleus or the protons was actually what made the periodic table periodic. And so you can sort of see one of the first examples of how they're mapping these radioactive decays, where they're seeing these nuclei change from one element to another, and realizing that this is sort of the reason for the periodic table is protons changing, or the number of protons. And then now we get to the Pauli part of my talk. So physicists are measuring beta decay. That's what the spectrum down here sort of shows. If you were to measure beta particles' energy in an event and you were to put it in a histogram, you would get a histogram of events that look like this. So you get a continuous distribution of beta energies. It's not always the same number. And so you would expect that when an element decays to another element, we know the energy levels of those elements is a fixed quantity. And so you would expect that the energy coming out of that decay would always have to sort of be equal to that fixed quantity. And it's not. Or at least it's not if you only look at the electron. And so physicists were puzzled by this because they thought that they could see all of the particles coming out of this decay. And they were really, some people were talking about abandoning the law of conservation of energy, which is a big no-no in physics, right? And Pauli instead says, maybe there's just another particle we don't see, right? And so that's the birth of the neutrino. And he writes this letter. He didn't go to the conference, but he proposed the particle basically in a letter that was taken to a conference. And this is a translation, which is, I think, in German. Yeah, probably. But I sort of translated it in sort of modern speak now. So it's like, in light of the data from beta decay, I have hit upon a desperate remedy. He literally says that. To save the conservation laws, I hypothesize the existence of a new neutral particle. He guesses its spin 1/2. He thinks the mass is roughly that of an electron, but that it's, because it's neutral, then it can basically be very hard to detect. And then he basically says, can you guys look for it? But he kind of low-key thinks that it's not possible to even detect. And so that's his, I think he actually says that in here. The reason it's a kind of a desperate remedy is he kind of thinks it'll never be detectable. Anyway, we'll get to the fact that it obviously is. So then, of course, history would have it that the neutron was discovered, and Pauli by accident named it the neutron as well. But there's this confusion. Pauli called it the neutron. A neutron was found. It was way too heavy, and then so they basically said, okay, so there's a big neutral particle and there's a light neutral particle, and so then the neutrino got named neutral little one, which is what neutrino means. Okay, and then Fermi, the brilliant theorist, sort of says, well, if neutrinos are present in beta decay, neutrinos must be in these reactions as well, and they must be able to, so he basically says, here's your traditional beta decay, but you can also have electron capture, which produces a neutrino, and you can have inverse beta decay where you can capture a neutrino. So that all just comes out from the theory. And so the detection of neutrinos comes in 1956. So this is a brilliant experiment. Rains and Cohen go to a reactor, which is producing tons and tons of neutrinos. And so they're going to look for this inverse beta decay where an antineutrino captures on a proton, and it's going to produce a positron and a neutron. If you do this on water with lots of hydrogen, then you basically produce a free neutron. So you're not changing you're not changing a big atom's nucleus. You're actually just producing a free neutron because hydrogen is just a proton. So you're not. You'll see. So the antineutrino comes in, it hits water, it hits the hydrogen in water, it creates a positron. Positron is an anti-electron. And so it's going to annihilate as soon as it finds another electron, which are all over the place in regular matter. And so it produces two back-to-back gammas. These are photons, basically. And then it produces that free neutron. That neutron bounces around because not many atoms want to capture a neutron. So it just sort of bounces off them like billiard balls. But cadmium actually really likes neutrons. And so it'll bounce around and hit water, and it'll hit steel and all the other things in your detector and just bounce right off. But if it finds certain elements like cadmium, it will capture on it. Okay, so the experiment, the way it works is you've got two big tanks, A and B, of water. And so that's what you're trying to get this neutrino to hit basically a proton in that water. And then you've got these other three tanks, 1, 2, 3. These are the scintillator that are doped with this cadmium. And so what the reaction you're trying to see then is create this positron, back-to-back gammas. You want to see these gammas in two neighboring detectors of the tank that you capture that neutrino on. So if it goes in A and captures, then you would want to see a gamma in 1 and 2 at the same time. And then the neutron is going to bounce around until it goes into one of those tanks and it finds a cadmium atom. And then it's going to create a huge amount of energy, 9 MeV, a few milliseconds later. The reason this experiment is brilliant is because when you do rare event searches like they're doing, you need to be able to say, I saw the signal I'm looking for and not a background event. So you're battling the fact that you've got cosmic rays coming from the sky, hitting all of your detectors constantly. You're battling the fact that all of the materials there are got uranium and thorium in them, and those are creating gamma rays and all kinds of other stuff in your detector. So you need a signature that is unequivocally the signal you're looking for, which is what they can do with, you see these back-to-back gammas, detector 1 and 2 fire at the same time. A few milliseconds later, you look for 9 MeV of energy in detector 1 or 2 or 3, it doesn't matter, because a neutron can bounce around for a while. But that's your signature, and that's a guaranteed signature for a neutrino capture. And so that's what they did. Obviously, they got the Nobel Prize for that. It turns out, I didn't even know this until I did the research for this talk. Ray Davis, if you know the name, is another neutrino, this is another famous neutrino experiment called the Homestake thing. He's at the exact same reactor as Rains and Cohen, actually, trying a different technique where he captures a regular neutrino on an electron, or sorry, yeah. He's basically trying to capture a regular neutrino on chlorine, and it produces argon. And then the way you tag it is you look for the radioactive argon that it produces. And he doesn't see anything. And so he's frustrated, and obviously Rains and Cohen get the Nobel Prize for doing almost the exact same thing. But he then says, well, the sun produces a ton of neutrinos, regular neutrinos, right? And so maybe the difference is that the different kinds of neutrinos. And so these plots or this bottom thing is sort of all of the reactions that happen in the solar model that produce neutrinos. So, and it also produces all of the heavy elements, right? So anything heavier than iron is produced in a supernova, but anything sort of heavier than helium is produced in the sun, like ours, right? And so this is sort of that production of lithium, iron. But it produces a ton of different neutrinos. You can see the red. And these are the top plot is this sort of spectrum of all of the neutrinos that the sun produces. That was the expectation anyway. And so Davis builds a much, much bigger experiment because now he's looking for a weaker source, you know, the sun as the neutrino source. So 100,000 gallons of, this is a dry cleaning fluid apparently. I don't know what the chemical name of it is. And the prediction is if everything goes well, he's going to see 1.3 argon atoms produced per day. So he's in 100,000 gallons of this fluid. He needs to find 1 atom a day. And he ends up measuring 0.48 on average, right? He runs this experiment for 30 years. And they captured 2,200 atoms total, measured 2,200 atoms total. So obviously a very technically challenging experiment. The way that sort of worked is here's that fluid tank of 100,000 gallons, and they bubbled helium through the tank to sort of pull out gases like argon. And then they would circulate the gases with the helium up to some way to separate the two gases. Helium is easy to separate from argon because they freeze at radically different temperatures, basically. And they would take that frozen argon and then they would take it over to a different detector and sort of look for that argon decay, which is an electron capture decay, about a keV of energy. So it's fairly easy to detect once you've separated. But really the challenge is figuring out how to separate the argon and how well are you doing that. 100,000 gallons of fluid, 1 atom a day. So Davis obviously gets a Nobel Prize for this work. And I guess, maybe I didn't emphasize that enough. He expected 1.3 atoms from the solar model, and they got a third of that. So that's a big problem for either the solar model, you would think, or his experiment. But it turns out it was neither. There was something wrong with the theory of neutrinos. And so this was the first hint that there's something beyond the standard model. There's something wrong with our understanding of neutrinos, because we sort of thought that the solar model was right at this point. And so here comes this brilliant SNO experiment that definitively shows what the problem is with neutrinos. So this is in Sudbury, Canada. This is kind of where I did my postdoc, but not on this experiment. They basically built this giant water tank, and they surrounded it with PMTs that were all looking inward, looking for flashes of light, basically. The inner vessel is filled with heavy water, which is basically you replace the hydrogen in water with deuterium, so it's got an extra neutron. Very expensive. They borrowed it from Canada's reactors. I forget what, it was a very, very tense deal with the Canadian government to borrow this heavy water because it's very precious. And the reason why this is a brilliant experiment is you can sort of you can measure the electron neutrino capture on deuterium. What it does is it turns a neutron into a proton. And it releases 1.44 MeV. So this is called the charge current reaction. But you can look for any other flavor of neutrino. And it turns out there's a flavor of neutrino for every lepton. So there's electrons, there's muon, there's tauon, leptons. And then there's a corresponding flavor for the neutrino. Any flavored neutrino captures on a deuterium. it could break it apart. So it doesn't convert anything. It just adds enough energy to break apart the deuterium, and it releases 2.2 MeV. So now we have a way. Well, here is some awesome pictures of them building the snow experiment. And this is 2 kilometers underground. Again, underground is a theme for all of the research I sort of do because we need to get away from cosmic rays. But the results of the experiment are here. So this is Ray Davis's experiment. He sees that deficiency. This is the theory. This is the result, the experimental result. Water sees the same problem. Other experiments doing gadolinium see the same problem. And then snow comes along and says, yeah, we see what you see. We see the electron neutrino flux is low, but we see that when you look at all of the neutrinos coming out of the sun, it does match expectation. And so that basically definitively proves that neutrinos can change flavor. So they can actually change, essentially the flavor state that it's in. And so the only way that's possible, I unfortunately have to show you a little bit of quantum mechanics, is that there is some sort of translation matrix between mass states and its flavor state. And the reason why we need to bring in mass states is because all particles that propagate through space must have sort of a, they propagate in their mass state. Any massive particle does. It needs to have this momentum in this propagator. And so we ended up having to create a matrix that sort of explains how the flavor state and the mass states are related. And a lot of experiments have been dug into the details of these parameters in this matrix. And so I like to show this plot that sort of simplifies this as much as possible. This is the probability of detecting something that was emitted as the blue curve is an electron neutrino. So basically at 0 distance away from the emission, you would expect no flavor change to occur. But as you propagate in space or energy, they basically oscillate between the electron neutrino probability goes down and the other neutrino states go up. And it turns out Earth, for the neutrinos that Ray Davis was looking at, are in this energy range. And so you can see that this is vastly reduced for the electron neutrino. So the chances that an electron neutrino emitted from the sun is detected on Earth this distance away is much, much lower than expected. So basically we found now the parameters of this matrix largely through what are called oscillation experiments. So this is a simplified model where you ignore basically many of the terms that are subdominant. That's what the full oscillation parameter looks like. It's just got a higher frequency thing, but since you're not sensitive enough to any particular band, you never see the high frequency oscillation. I just wanted to show you a couple experiments that sort of teased out some of these parameters of the neutrino oscillation. So there are experiments that produce neutrino beams, muon neutrino beams, by hitting protons onto targets. They produce a bunch of crazy pions, and then they basically shoot those pions into whatever, the Earth basically. And you shoot them through the Earth so that nothing except neutrinos can propagate through it. And the idea there is now you've got a pure neutrino beam going 295 kilometers through the Earth to your giant detector. And this is T2K, so that's the Kamioka detector. And just give you a sense of scale, this is people in a boat in the Super K detector. This is what they were shooting those neutrinos at. And what they were looking for was muon neutrinos turning into electron neutrinos and measuring those oscillation parameters. There are two experiments that are sort of currently being built that are continuing this sort of beam line type experiment. So almost the exact same setup. We've got J-Park in Japan shooting at a new, bigger detector. So this is the cavern they mined out for the Hyper K, they call it. And they're going to shoot muon neutrinos again at that and try to determine more of the mass of the, like higher precision of the matrix element. And I guess sometimes it's imperative to show people the timeline. They hope to turn on in 2028, so in our lifetimes. And then the Dune experiment is another one. This is the biggest program in the US right now for high energy physics. And they're going to shoot muon neutrinos from Fermilab to a mine in South Dakota. And so they've mined out 2 big caverns to put 2 40-kiloton argon detectors in there. And they hope to turn on in 2032. So they will not be first. I'm going to skip this slide. Okay. So that's sort of, I would say, where we are now with neutrino physics. And now, you know, those were precision measurements largely, Dune and Hyper-K. They're going to maybe tease out some of the parameters we don't know yet, but they're not going to tell us anything new beyond the standard model, let's say. So I mentioned double beta decay. This is what I did my PhD on. The detector signal we're looking for is if this is 2 neutrino double beta decay, so that just like in beta decay, you get this continuous spectrum because neutrinos take away energy. In 2 neutrino double beta decay, you also get this continuous spectrum, but then the neutrinoless mode would be a delta function or a peak right at the Q value because there's no neutrinos. And so that's what we have to build our detector to look for. There's something like 12 isotopes that do this kind of decay that you could imagine doing this experiment with. My favorite is xenon, but there's also germanium and molybdenum common. So this is the detector we built. It was a very thin copper can. The idea to keep it thin is to make radioactive backgrounds as small as possible. And it was in a, you know, it was surrounded by lead so that we could also reduce as much as possible backgrounds. And skip that slide. So this is more or less what it looked like underground. I think I showed one picture already, but you know, we had lots of infrastructure down there to liquefy xenon for the detector and to support all of the cryogenic stuff and all of that. And this is what it looked like. So these are clean room modules actually underground. So we go underground where it's filthy and we build clean rooms apparently because we need basically the experiment to be in a dust-free region. And so then this is what the inside of the clean room looked like. And the picture is here. And then that's all of the support equipment for three or four rooms. I think one of the things that's underappreciated until you get into the weeds is how much work it is to build an experiment in terms of toiling in the lab. And now you all are getting a sense of that now. But you know, we've had to build lots of assay capabilities to find low background materials. There's a whole, you know, like at Snow Lab and lots of other labs, they have tons of germanium counters lying around that you can use to measure materials with. We had to make our own custom cables and our own custom feed-throughs. We even have, this is a cottage industry now, xenon pumps. Nobody makes xenon pumps commercially. So it turns out physicists make xenon pumps. And so that's something I do a lot, is make xenon pumps. A bunch of really neat pictures of us doing things. I'm a forklift driver of all things. So that's me driving a forklift underground. Like I said, we do lots and lots of manual labor. This is some poor grad student is mining salt here that I took a picture of because the salt actually heaves and we had to basically keep the drift clear so that people can egress and get in and out and stuff like that. EXO 200 ran from about 2011 to 2019. So this is us taking the detector out. So we don't have to be clean anymore. In fact, it's now lying in some machine shop here at SLAC, this detector. Yeah, that was its final day. And this is what we sort of measured in the end, right? So this gray band is that double beta decay. So that's the standard model process. And these other spectra here are backgrounds that we measured. And what we're looking for is a peak right here, which we clearly don't see. So unfortunately, we set a best limit, but no sign of double beta decay, neutrinoless double beta decay. So we push on. One of the things I work on now is XLZD. So it's a future, we're combining basically the dark matter xenon world with the double beta decay xenon world, because we both want to build a large low background xenon detector. And so it won't be enriched like EXO was. So it'll only use a natural abundance of xenon. So it's only 9% of the isotope that double beta decay people want, but that's fine. You can see it's massive. So this is sort of to scale a person next to the detector. It's 3 to 4 meters tall. So I guess right now we're just sort of understanding what the design needs to look like to do the physics we want to do to push it to the next level. Okay, so there's a few mysteries about neutrinos. We still don't know their mass. And you might guess that you could just measure the mass through kinematics. Now that we know what the whole process is, what you would expect to see is, if this is the beta decay spectrum, you would expect to see at the very end a shift, because the neutrino, if no energy, it still has its rest mass. And so it just slightly tweaks the beta decay spectrum from what you would expect. And it turns out there's also a huge cottage industry doing this. The problem is it's very difficult. So you can maybe appreciate how zoomed in this endpoint is of this beta decay. But we're basically looking for 1 part in a million change in the beta decay spectrum. And that's just because we know the neutrino mass is much, is lower than 1 EV now. And so that the amount that it changes the spectrum is minuscule. So this is the experiment that's sort of world leading now. This is a vacuum vessel that they're trying to take to the site. And so, of course, this is in Germany, and so they have to get through these old cottages. And of course, the local town loved it when they sort of tried to bring the spectrometer. Of course, they planned all this, and it's exactly the size it needs to be to get through that. But yeah, it was a real event. As you can see, every single person from the town came out to watch them bring the spectrometer through their town. The sensitivity of Catrin will eventually, by the end of its run, which it's running right now, should sort of reach 0.2 EV, but there's a good chance that the neutrinos are lighter than 0.2 EV, and so it will just set a limit. And unfortunately, this technique is sort of limited by the size of that object. If you want to go better than 0.2 EV, you need to build a bigger spectrometer, but you can tell it's already rather big. This is essentially what's going on. So that is the spectrometer that they were wheeling through the village. But what happens is you take tritium and it decays here, and the electron, if it's perfectly aligned with this beam, the electron will go through all of this filtering and stuff, and then it'll go through that big spectrometer. And if it's exactly at the energy they tuned it at, then the electron will get all the way to the end. Otherwise, it won't make it through this. And you'll see that electron here. And so what you're trying to do is you basically set the energy that gets through, and you just sort of count the number of electrons here, and then here, and then here, and then here. And looking again for that tiny little deviation. This is a project that I'm sort of dabbling in now, and it's another way to do this endpoint measurement. The idea is, instead of building a big spectrometer, which is prohibitively difficult, is to instead use what's called cyclotron radiation. So if your tritium decays and it ejects an electron, you can basically do that experiment in a magnetic field, or have this decay happen in a magnetic field. Electrons in a magnetic field will produce cyclotron radiation. And so basically it'll be a radio frequency signal that you can look for. And if you can measure the frequency of that, you can measure the energy of the electron, assuming you know the B field, the magnetic field. sort of guess is that this kind of technique can get us down to 0.04 EV neutrino mass. So that's definitely a step beyond what Katrin can do, but this project is definitely still in its infancy, but look forward to it maybe. And then I'd like to say this about cosmology. This might be controversial, but cosmology will certainly measure the neutrino mass before an experiment does, I think. I mean, I was hoping for this project called CMBS4 to happen, but it got delayed, if not canceled. But eventually cosmology is taking enough high quality data that they will basically say the neutrino mass has to be below this for cosmology to work. But I don't think anyone's going to believe it until we measure it in the lab, the mass that they get. And so I hope they tell us what to look for, you know, what the mass range should be. But I don't think that gets us out of having to do the hard experimental work. And I think one of the reasons why I find that to be true is because cosmology sees this whole picture and it's trying to say something about 1% of it, right? So neutrinos are just 1% of the normal matter. And so that the model they're fitting is just not well tuned to just that one parameter. And so they will never have that strength to believe the answer to the point where we wouldn't try to do it experimentally. I'm also doing other work here with cryogenic detectors. So cryogenic detectors are really cool because they're really good at measuring very, very tiny energy depositions. And so we can actually look at nuclear recoils of reactions like electron capture. So we basically, what happens is certain isotopes will go under electron capture and produce a neutrino recoiling against against its nucleus. And so if you can measure nuclear recoil very accurately, you can also probe the neutrino. So we are sort of looking for sterile neutrinos with this technique, but in principle, you can also try to measure the endpoint energy and try to determine the neutrino mass. So yeah, these are sort of the detectors that we implanted with electron capture isotopes and are running here in building 33 in the cryo lab. Okay, I think I'll swing back around now to the practical, and maybe we'll even have a couple minutes for questions. But how did I get to work at SLAC? Maybe some of you want to work at SLAC and want to know what the secret is. Well, I would have to say my grades and my schools are not all that impressive. But I had demonstrated getting shit done, I guess is what you would say, in the lab. And so I had a pretty decent history of doing that. I became an expert on all of EXO 200 systems as a grad student, even though I was doing AMO physics for my thesis. I worked a lot underground on the experiment. And then I think luck played a part. You know, we were underground at a mine that also did waste disposal for the DOE. And so LANL would send us stuff that they used to make nuclear bombs with, not us, but like the mine. And they would put it in the other side of the mine, and they basically just dispose of it forever, is the idea. And Los Alamos just sent a dirty bomb to WIP, and it blew up underground. And so they shut us down for 1.5 years. And well, they had to clean up the mine basically. And so when we wanted to restart, I basically told SLAC, like, you need somebody on site to just do all of the things that need done, because what we were typically doing is nobody lived at the mining town. So we would just fly people out for 2 weeks at a time, and it was not a very efficient way to run an experiment. And so I offered myself basically to live in the little mining town. I'm from New Mexico, so it was fine for me. And basically get the experiment running, and SLAC hired me. So is there a conclusion to my talk? Well, neutrinos are interesting, I hope, is one, but pursue your passion, I think, is one of them. We like to say this, at least in our group, if you enjoy what you're doing, it's not work. Don't turn away from challenges, though, or hard work. So we often had to do a lot of hard work, manual labor, in fact, to keep the experiment running, but it was, in my opinion, always worth it. And always be learning. I think one of the things for me was the number of skills I acquired in running X200 opened that door for me where SLAC saw me as an asset to just hire me and move me to site. I like to also pitch this book. If you're interested in the DOE and how National Labs sort of got started, this is a great book, and the audio version of it is awesome. The narrator is really good. This is basically, if you've seen Oppenheimer, right? It's a very small fraction of what's in this book. And this book is great. And this is the final picture. Why a bunch of physicists are crawling around looking at the sewage treatment plant, I don't know. But yeah, I think we have 10-ish minutes now. Thank you.